The broadcast is now starting. All attendees are in listen-only mode.
Hi there, and welcome from Ventura, California to GNSS-Denied Environments, Living in a Vulnerable World, sponsored by Novatel and Inside GNSS and hosted by WebAttract, your end-to-end solution provider for informational webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they discuss the topic of GNSS-denied environments and pose solutions for operating in GNSS-denied or impaired environments. We'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Experts panel session with all of our panelists. Now, we've invited you, along with over 650 professionals from 57 countries and 33 states and provinces representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident you'll find today's webinar of value. Before we get started, Glenn Gibbons, editor and publisher with Inside GNSS, would like to take a moment to welcome you and introduce Neil Guerin and Demos Gebra-Exabher, who will be moderating the main portion of today's webinar. Glenn?
Thank you, Roy. And greetings to our global audience from all of us at Inside GNSS magazine, and welcome to this latest installment in our web seminar series. Today's presentation is sponsored by Novatel and addresses a subject that is generating a growing concern within the GNSS community. That is, the possible need to operate in situations and environments in which GNSS signals are unavailable or unreliable. Inside GNSS reaches more than 35,000 readers around the world with its print edition, and thousands more with our digital magazine and newsletters. Based on the number of registrations for today's webinar, it's clear that GNSS-denied environments are a subject of considerable interest to our audience. Now I am pleased to invite Neil Guerin, the Aerospace and Defense Product Manager for Novatel, to say a few words about today's event. Neil?
Thank you, Glenn. Novatel has been designing and delivering precise GNSS equipment for over 2 decades, and from the beginning, interference to GNSS has been a concern. Customers around the world have come to depend on GNSS for an extraordinary number of different applications, and solution availability is always at the top of the list of must-have features. Today you will hear how denial of GNSS, whether unintentional or intentional, can significantly affect position, navigation, and time solutions. Our panelists will discuss the need for resilient PNT for varied applications and end users, including maritime and aviation safety applications. We will also hear about some of the different techniques to mitigate against interference, including equipment design techniques and backups to GNSS. On behalf of Novatel, welcome and enjoy the webinar. Back to you, Glenn.
Thanks, Neil. Our moderator for today's web seminar is Demos Gebra-Exabher. Demos is an associate professor of aerospace engineering and mechanics at the University of Minnesota, Twin Cities campus. His research deals with the design of multi-sensor navigation and attitude determination systems for aerospace vehicles. More recently, Demos' work has focused on multi-sensor solutions for operations in GNSS-stressed and GNSS-denied environments. Demos, it's great to have you with us again today. Welcome.
Thank you, Glenn, and welcome everyone, and we're glad you could join us for this webinar we're having on the issue of operation in the presence of stressing and denial of GNSS. We have on our panel today 3 leading experts on the issue. They'll be discussing the general issue of GNSS denial and also how specific user communities, in this case marine and aviation communities, are dealing with this issue. Before I introduce the panelists, I would like, however, to take a chance to do a poll to sense how our audience sees this issue. So, Lori, if you could put the poll up.
Sure, Demos. And folks, coming up on your screen right now, you should see the question. Looking forward 5 to 10 years, do you think jamming and or spoofing will impact operational use of GNSS? And if you would please select just one. Yes, widely occurring. Yes, occasionally occurring. Or no, because there will be redundant GNSSs operating. So go ahead and weigh in on that if you would. Why don't we go ahead and close up that poll? All right, there it is. What do you think?
All right, so it's interesting that there, I guess about 3% of the users that think that because of redundant GNSSs we will not have an issue, and actually that's a key issue that we want to talk about today, is to show that this is going to be an issue even in the presence of multiple GNSSs. So with that, let me go ahead and introduce our first panelist. We'll talk about the general GNSS denial issue. Our first panelist is Logan Scott, who has nearly 35 years of military experience in civil and GPS systems. He's a private consultant specializing in radio frequency signal processing and waveform design for communication, navigation, radar, and echolocation. He has been an active advocate for improved civil security through the test-based GPS receiver certification, crowdsourced jamming detection, and location, J9 location, and by adding robust signal authentication features to civil GPS. At Texas Instruments, he pioneered approaches for building high-performance jam-resistant digital receivers. Logan holds 35 U.S. patents. Logan?
Well, thank you for the introduction there, Demos. This morning I'm going to talk mainly about jamming, its origins, effects, and mitigations. And a lot of times people think that jamming is primarily a military thing, but we're seeing it in the civil sector now, so I'm going to focus on that as well. So why is GPS so sensitive to jamming? Well, if you take a look at the satellite up here, it's got a 25-watt transmitter feeding into a 13 dB gain antenna, or stated another way, roughly a factor of 20 gain there. So to first order, it has about the same parameters as a cellular base station, which is normally expected to cover a range of a couple miles or so. With GPS, though, our range is about 12,000 miles, and so to put that graphically, that's basically going from LA to DC about 5.5 times. So the satellites are quite far away, and a consequence of that is that the signal arrives at Earth really quite weakly. In fact, the L1CA signal, the primary civil signal, arrives at a power about 100 times less than thermal noise. And so the bottom line is that the received signal is weak, and that makes it fairly straightforward to jam. So why would someone jam your GPS? Well, in the military arena, it's pretty obvious. You'd go off and deny navigation to opposing forces so that they're less effective, and it creates confusion between the various sensors and so on. In the civil arena, we've seen jamming accidental, but we're also beginning to see quite a bit of deliberate jamming. And for the uninitiated, you might think, well, jamming is a terroristic exploit, but actually it's mostly done for financial reasons. As an example, if you're stealing a high-end car, it's a really good idea to have a GPS jammer in there so that OnStar and LoJack and things like that don't work. So again, financial motivations are quite strong. So are we actually seeing jamming? Well, here's some data that came out of the FAA last year. And basically, these are different WAAS reference stations. And this is the number of events that were longer than 30 seconds at various stations. So, for instance, this is Miami here, this is Kansas City, and here's Manchester, New Hampshire. Now, I'm not trying to pick on the WAAS reference stations. They're actually quite good. They maintain very good situational awareness, but they provide an excellent source of data as far as whether or not we're seeing jamming. And one thing that's kind of, One thing that's kind of interesting is the reason that we're seeing a lot of jamming at these stations here is because they're located near major highways. And so the jamming events are typically vehicles driving by and causing jamming. And typically what is in the vehicle that's causing the jamming is a personal privacy device, or basically a little cigarette lighter GPS jammer. Now, this problem is not unique to the U.S. If we look at the Taiwan International Airport, they're seeing about 117 events per day. And in fact, in general, you tend to see more jamming around ports of entry, shipping ports, airports, things along those lines. So we are actually seeing jamming now. So with that said, what effect does this have on vehicles that are out there? And so I'm going to focus on aircraft for the moment. Here's a typical aviation antenna. And what you see here is a gain pattern for that antenna, where basically this is directly above, this is off to the horizon here, and basically this is showing the gain here. Now what I've got down here is various types of jammers ranging from personal privacy devices, say around 100 milliwatts to 1 watt, and then over here some higher power jammers getting into the 10 watt range there. Now the first case I'd like to cover is the situation where we're flying straight and level. And so the first order, that corresponds to the yellow cases here. And basically this is the amount of energy or range associated with generating a JORS of 24 dB, which can be fairly damaging. So if I'm flying straight and level, then minus 10 dB corresponds to this yellow case here. And so even this 100 milliwatt jammer can cause significant jamming effects at a 3-mile range. And if we talk about a 10 watt jammer, we could be talking ranges upwards of 30 miles there. Now, as you get close to the ground, when you're in the landing phase, that's when you typically do a lot more maneuvering. And so the horizon, you're actually going to develop fairly significant gain in that direction if you're in a standard 30-degree bank. And so that corresponds to the blue cases here. And so even this 100 milliwatt jammer, it can have an effective jamming range of almost 10 miles, and the 10-watt jammer, an effective range of around 94 miles. Now, having said that, earth obscuration is going to limit your range, but I think you can see at this point that the jamming can be quite significant in its effect. Okay, so in the prior chart, I was talking primarily about free space propagation, what happens in the ground-to-ground environment. Well, these are various propagation models across here, and the one I'm going to focus on now is the HADA urban model, and this is associated with building median height of around 50 feet. And basically what you see there is that the same jammer, a 200 milliwatt jammer, has an effective range of only about 500 meters, as opposed to, say, 45 kilometers for ground-to-air kind of configuration. So what this is saying is that the range of a jammer varies tremendously. And this is ultimately going to make jammers quite hard to find, particularly if you're trying to find them while you're located on the ground. Okay, so with that in mind, another major issue that we have to take into account is the fact that in many cases, people are not necessarily using the authorized equipment. Military troops very oftentimes use these commercial units here. They like them a lot. If you go into an aviation cockpit of an aircraft 10 years old, think about your cell phone 10 years ago. Remember what it did? Compare that to the one you have now. Well, same thing has happened in aviation avionics. And so very oftentimes people unofficially upgrade their cockpit by putting in an iPad or an Android device and using that for navigation. And then in ship applications, very oftentimes these are much easier to use, these Android apps, if it's located up on the bridge and you use the Android device as opposed to the official equipment. So there's a significant risk, and I'm not sure how to quantify it, but it's worth noting in this discussion here. So what can we learn from military signal protection methods? To first order, I would describe military protection methods as a bunker defense. In other words, they have a signal, a particular signal, and they want to get it. They want to receive that signal. And the first and one of the very important things to do is to reject out-of-band signals. The GPS signal transmitters are only about 31 megahertz wide. I'm talking about the satellites. And so anything outside of that 31 megahertz range is really not of interest to the GPS receiver. So use as narrow a filter as you can. Maintain situational awareness, very important. Know the fact that you're jammed and respond accordingly. For the military user, they like to avoid relying on civil signals, mainly because there are a lot of vulnerabilities with those signals because they are published formats. There's no security features on those, and so as a consequence, they're very easy to generate spoofing signals. Now, another very important technique is to integrate with an inertial measurement unit so that when you are jammed out, you can ride the inertial, but sort of also used at the same time is this notion of vector tracking, in other words, tracking the satellites jointly. Now, for the civil user, vector tracking could be very important even if you don't have IMU-8ing, because vector trackers, they're actually quite hard to draw off, as opposed to scalar trackers like phase lock loops and DLLs. They're pretty straightforward to draw off. And then finally, by creating nulls in your antenna pattern in the direction of jammers, you can get a lot of jamming resistance using that technique as well. Now, with this all said, it's important to understand that most of these ECM techniques do degrade your accuracy. And in particular, the real-time kinematic stuff and adaptive arrays, they don't play together very nicely. It's possible to do that, but you can't just take an antenna, hook it up there, and expect things to work. So again, very important to recognize most of these techniques will degrade your accuracy in one form or another. Now, if you're a military user, one of the things you might consider doing is blowing up the jammer. And that's certainly possible to do, but it's important to recognize that the complexity of a jammer is roughly the same as that of a microwave oven. So if you're shooting $1-million missiles at microwave ovens, the economics are not going to work out very well for you. Okay, so with that said, let's talk about adaptive arrays a little bit more. This is a kind of an old chart here. This is circa 1990, but it illustrates something very important. Basically, here's the antenna array, and here's the antenna electrons, which does the adaptation and so on and creates the nulls. This has effectively been reduced down to a chip in many applications now, and so the size, weight, and power on that is really quite small. but the array itself is still quite large, and the reason for that is physics. The antenna elements need to be about 1/3 of a wavelength apart, or roughly 4 inches apart, and so the physics is such that the adaptive arrays are still quite large. So in portable applications, adaptive arrays are actually quite hard to employ. Another very key thing that I had mentioned was the situational awareness issue. And basically, if the receiver reports interference to users, then the users can take appropriate actions. So as an example, if I've got a handheld unit and it tells me I've got jamming and how much jamming I've got, then I can basically rotate myself so that I put my body between the receiver and the jammer and create a null using my body. And that's actually a very effective technique. Perhaps more importantly, if you maintain situational awareness, the receiver can avoid generating hazardously misleading information, or HMI. And the particular issue you get into with HMI is if you report a position and it is incorrect, then people will go off and do things incorrectly based on that incorrect information. So it's much better to say, I don't know where I am, as opposed to report a position and say, here's where I am, and have it be wrong. Another thing that happens with situational awareness is, particularly if you have comm capabilities or communications capabilities, you can report that to IDM or interference detection and monitoring systems, and they can actually locate the jammers. And so as an example, I've got a jammer located at the center here, and this is showing J over N as a function of location in Y and X. And so as you might expect, a cell phone which is located close to the jammer sees fairly strong jamming, whereas one that's located more distantly sees a lower level of jamming. Well, if you have the aggregate of information from these various cell phones out there, you can actually make a determination of where the jammer is with quite good accuracy. And the thing is that there's a lot of these cell phones out there. 1,000 cell phones per square kilometer is not an unusual count. And it looks like you could locate jammers quite accurately in real time as they move around, perhaps for enforcement actions. Okay. Now, when we were talking about the WAAS receivers, one of the things you might have noticed was it says it was detecting these based on AGC. So let's talk about that a little bit. It's very important. In most receivers, you do a conversion down to a low IF frequency, go through an amplifier, and then you go into an A to D conversion process here. And for most GPS receivers, they use what's called a 1.5-bit A to D converter, where if the voltage is above V sub B, it puts out a 1. If it's less than minus V sub B, it puts out a -1, and otherwise it puts out zeros. And you might say, well, that's pretty low precision A to D conversion. Well, yeah, it is. But keep in mind, the GPS signal is 100 times weaker than the thermal noise, and so as a consequence, a lot of precision is not needed in the A to D conversion process. However, you would like to see about 40% ones and -1s out of this process to maintain good signal-to-noise ratio. And because of variations in front-end amplifier gains and so on, it's very common to have an AGC in there, an automatic gain control, which basically controls the gain of this amplifier in a closed-loop feedback fashion. So if it sees too many ones and -1s coming out of this process, basically what happens is this gain is going to be reduced. If I see too few ones and -1s, then I'm going to increase the gain. So what's that got to do with jamming? Well, if you look at this control voltage here, this can tell you an awful lot about what's going on in your jamming environment. Now this little element here, I'll come back to that in a second, but let's take a look at what happens with jamming. So I've got jamming turning on and off at 100 Hertz rate. So the total duration along this axis here is 50 milliseconds. And so when the jamming is turned on, what you see is that the gain goes low. When the jammer turns off, the gain goes high. And so basically by looking at the gain of your AGC, you can make a pretty close determination as to what the jam-to-noise ratio is. Very useful for situational awareness. If you see a pattern like this in your gain, you know that you've got some kind of jamming going on there. Now, as a bit of a refinement on that, you can set up an additional threshold. In this case, I'm using 1.3 V sub B. And basically what this is doing is it's mapping out the probability distribution function of the jammer at another point. And the Gaussian jammer would have a bell-shaped curve, whereas a constant envelope jammer, for instance, a continuous wave or a gold code jammer, has an inverted bowl format. And so you can actually make a determination as to whether or not you've got a CE or constant envelope jammer based on that channel there. And so in this case here, I've got CW turning on, and you notice how this channel goes very low in that case. So again, you can make a determination as to what not only what the power of the jammer is, but also what type of jammer you've got going on. Okay. Now, something else that you should be looking at is range Doppler maps. And so basically this is the Doppler, this is the range, and so if your radar type, this is basically the ambiguity function, and in this case here, I've got a J over S of 24, which if you recall back to the aviation case, that's the number I was using. One of these is the real signal. The rest of these are all bogus. There should be only one spike here, and in fact, I happen to know it's this one right here. That's the real signal there. So by looking at your range Doppler maps, you can make a determination as to whether or not you've got jamming going on. Now, you might consider doing some heroic measures trying to figure out which one's the correct peak, but in many cases, it's better to just say, well, I can't receive that signal, and so I'm not going to use that in my navigation solution. That's oftentimes the better solution. Okay, so with that in mind, what should the civil user do? Well, basically, they should discard jammed or spoofed signals, and in order to do that, they basically perform a series of sanity checks along the lines of what I've discussed so far, but also they should go off and try and authenticate the signals. In other words, establish whether or not it's really coming from a satellite or not. So as an example of a sanity check, if I see high jamming and high signal-to-noise ratio at the same time, that's a pretty strong indication of spoofing there. So discard that signal. Don't use it. And there's a lot of opportunity to go off and discard signals in the current environment. For instance, in GPS, we've got the L1, L2, and L5 frequencies. So unless a jammer and or spoofer covers all of those signals there, you're going to have some uncovered vulnerabilities there. And so if you get a result from the L1 signal that's very different from the L2 signal, you might not want to use the signal that's being spoofed. You can also do cross-checks with GLONASS, Compass, or actually now BIDAO, and Galileo. Interestingly, Galileo actually has some signal authentication features proposed for it, and we may actually see that in the future. Additionally, if you're a cell phone user, very oftentimes you have access to Wi-Fi looking for access points to determine your location, cellular time of arrival, TDOA techniques. In a iPhone 4, the inertial measurement unit, which is 6 degrees of freedom, is only $3.35. And so if the IMU says you're going north and the GPS says you're going west, again, pretty good indication that something's going on. In other words, you're not seeing consistency. You can also consider using the MAG compass in there as part of your solution, and also point space databases. Google, when they send out that Street View camera, it also collects a point space database, and potentially that could be used as a way to confirm location. Now, George Shaw, our next presenter, is going to have some very good information on eLoran, so I'm not going to steal his thunder on that, but he's got a really cool story to tell on using that as well. So just to summarize, what we want to do is we want to look for uncorrelated vulnerabilities between our various inputs, if you will, and then look for consistency between those. And in all of this, at least for the civil user, size, weight, power are very important. But also export restrictions can be a major consideration. And in particular, adaptive arrays very oftentimes operate under ITAR restrictions or international trade and arms regulation. And so they can't be exported. So again, if we look at a typical cell phone, it's got all of these blue elements in here, and it can look for consistency there in order to determine whether or not it's got a good navigation solution. So when we look at the next generation, or actually I should say current generation navigation systems, there's tremendous opportunity. They use multiple signal sources going into them, and they could provide a more robust navigation solution by doing cross-checks between the various sensors in order to avoid generating HMI. And then as a final point, I should note that a lot of these devices, in fact all of the devices shown here, have a communications capability, and so they can report what they're seeing in terms of jamming, so that potentially we can generate real-time maps of jamming to improve situational awareness, not just for the receiver itself, but for any other users that happen to be out in that area. So with that, I'm going to turn it over to demos, and we'll get to questions, and George Shaw next.
Thanks, Logan. All right, so moving on, looking at the issue in the marine environment, our next panelist is George Shaw. George is a principal development engineer working for the Research and Radio Navigation Directorate of the General Lighthouse Authorities of the UK and Ireland. He's responsible for strategy and system studies that inform the future direction of maritime aids navigation. Mr. Shaw specializes in system engineering and analysis of robust GNSS-based solutions for positioning and navigation across air, land, and sea domains. He holds a MA in mathematics from the University of Cambridge and is a chartered engineer as well as being a member of the Royal Aeronautical Society. George?
Well, thank you very much, Demos, and good evening to everyone from the UK. I'm going to talk to you about the urgent need for resilient positioning, navigation and timing that needs to be put in place to protect the safety of mariners. Now, GNS denial in the maritime environment already severely impacts the safety of navigation, increasing the risk of collision and grounding of ships. Resilient PNT is now needed to mitigate the risks. Looking ahead, by 2020, the implementation of the International Maritime Organization's e-navigation will integrate and harmonize navigation information across the ship systems. So resilient PNT will be essential to safeguard future maritime operations using e-navigation. Okay, now I'm going to present the work of the General Lighthouse Authorities of the UK and Ireland, the GLAs. The GLAs shown here are responsible for maritime aids to navigation around the coasts of UK and Ireland. And Trinity House, responsible for England and Wales, was founded by King Henry VIII and celebrates its 500th anniversary next year. GNSS has become the mariner's primary aid to navigation, alongside lighthouses and buoys. GNSS is now at the heart of the safety and efficiency of all maritime operations. So the GLAs are prototyping maritime eLoran in the UK as an independent and complementary backup to GNSS. And I'm going to tell you more of the exciting eLoran developments in the UK later. Right, here I've got a picture of shipping traffic in the North Sea over the last year or so in 2012. Now, the waters of the North Sea contain a very high density of shipping. You can see the reports here from AIS over that full year. There are many traffic pinch points in the region at approaches to major ports such as Rotterdam and at gateways into the Baltic such as the Kiel Canal. So the risk of collision and grounding has been calculated, and you can see that on the bottom right. It's found to be greatest in the southern North Sea, where there's a lot of conflicting traffic, and the darker colours give the higher risk of collision. On the top right, you can see the picture of the English Channel. This is the world's busiest maritime choke point. There are some 500 vessels a day that pass through the Dover Strait. Now, those ships sail through British weather, often in low visibility fog, and with many vessels highly dependent on GPS for their navigation. So here the GLA's great concern is that GPS equipment and satellites can fail, and that the vessel's navigation is vulnerable to solar weather, accidental interference, or intentional jamming, with serious consequences. Now, the maritime world is going through a profound change, technological and operational. There's increasing competition for marine resources, demanding to share the waters that are used by shipping. On the top left there, you can see the many wind turbines that are being implemented and built in the North Sea. They're being erected to meet the need for renewable energy. By 2020, navigable sea space for ships is expected to be significantly constricted by wind farms, adding to the restrictions from oil and gas fields and from the environmentally sensitive areas. So the top right, you can see the map of the obstacles to shipping in the North Sea region around the UK, and it's very highly complex. Now, already officers on many vessels rely almost entirely on GPS, and by 2020, e-navigation will increase their dependence on electronic systems. When GNSS denied, traditional fallbacks such as paper charts and dividers simply won't be adequate. If e-navigation is to enhance safety and not actually reduce safety, then it's going to be essential to have at least two independent, robust sources of position aboard. And at the present, we don't really even have one. So is there a real threat? We saw from Logan earlier the amount of jamming that occurs at airports. Here's the results from some of the SENTINEL project in the UK, which was completed recently. It established a national network of GPS probes to monitor the quality of GPS signals for not only detection but also location of jamming sources. And the analysis of those detections is available in an online geographic information system. And that is showing daily GPS jamming events from vehicles, especially near ports. So now I want you to consider the effect of one of those jammers being operated on a vehicle ferry. Say it's on a ship navigating in the English Channel in fog. So, the GLAs have demonstrated what happens to shipping when a GPS jammer is deployed. The type of jammer that you can buy cheaply on the internet. Top right, you can see the jamming trial diagram from Flamborough Head, which disrupted GPS on vessels throughout this area of the red zone up to 30 kilometres out into the North Sea. On the top left is the GPS track of a ship sailing through the jamming beam. Here you can see total loss of GPS navigation. And even more serious, you can see examples of false positions and tracks that occur, some of them being wildly wrong. Now that same jammer on a cliff top near Dover would take out the whole of the Dover Strait. So in a later trial, we took a tiny jammer, less than 1,000th of the power of a mobile phone, aboard this GLA vessel again, and caused its GPS systems to give false positions and velocities. An autopilot linked to the chart display would have steered the ship off course without any warning. The first false positions that we got were credible but wrong. No alarms sounded. This is hazardously misleading information and very dangerous. With little more jammer power, every GPS receiver on board failed simultaneously. The chart displays showed the ship in the wrong position, and this was then reported over the IS to nearby ships and to the vessel traffic services ashore. The autopilot was disturbed, differential GPS was lost, the satellite communications failed, and so too did the distress system whose job it is to raise alarms and to guide in the rescuers. And when the crew responded as well-trained mariners should, reverting to good old radar and gyrocompass, then to their surprise they found that those systems were affected as well. So we learned that ships nowadays have multiple GPS receivers embedded in multiple systems in ways that no one on board understands. So, as the global economy recovers, the already crowded shipping areas such as the North Sea are going to need to carry more and bigger ships. The navigable sea space will decrease, and the ships will become more and more confined, with higher traffic density and more conflicts. The GLAs are working in the AXES project with partners in the North Sea region, pioneering a North Sea regional e-navigation testbed with resilient PNT. So with partners in Denmark, Germany, Netherlands, Norway and Sweden, AXES is implementing the testbed in the North Sea with resilient PNT at its core. AXES is investigating a mix of radio navigation fallbacks to GNSS. We're looking at radar positioning, medium frequency ranging mode from DGPS beacons, and at the core, the available system of eLoran. And those testbed demonstrations are planned to happen over the next 2 years. So, in the UK, the maritime community is raising cross-sector awareness of the GNS denial and the need for resilient PNT, and these issues through that awareness have hit the national headlines. The UK eLoran transmitter is already delivering resilient timing across the UK, and there's interest in developing resilient PNT for land mobile applications. Meanwhile, the threat's evolving, an increasing likelihood of GNSS spoofing, and we can't be complacent. We have to safeguard our critical national infrastructure, and I'll shortly explain how we're using eLoran to protect UK shipping. Thank you, Demos.
Thank you, George. All right, so we're going to take stop on the presentation a little bit for a while and give you the chance to ask the experts questions. And even though we haven't introduced them, Sherman Lowe and Peter Soar are also available to answer some questions. So let's look at the questions from our audience. All right, so the first question, which is for George, is from Neil saying, we are seeing a lot more interference issues in marine environments. What can we do to mitigate these effects where the frequency is usually the same, but the momentary pulses have random amplitude and period?
Our fallback is to maps and compasses and charts at the moment, and that is really quite difficult in foggy conditions. Those traditional fallbacks are not often practiced by mariners, and those skills can be really quite rusty when they come to be used. That's why there's a need for an independent means to GNSS that is complementary and will be brought into play when GNSS is denied or affected, so that we can have a seamless PNT that's available to all the ship systems.
Thank you, George. Let's see. So the next question is going to be for Logan, and it comes from Gavin. And the question is, while jamming and spoofing is a serious threat to prepare for, it has not been widespread or even increasing. just how much of the heightened awareness is a cottage industry or a solution looking for problems? Kind of an interesting one.
I think that's an excellent question. Part of the reason that we're not seeing a lot of increase, at least in the U.S. right now, is that the laws have changed as of March last year, 2012. Up to that point, it was legal to own jammers, advertise them on the internet, sell them, and so on. And since that time, the rules have basically become somewhat draconian. If you sell a GPS jammer, even one, over the internet or import one from another country, the potential penalty is $100,000 per incident. And so that has put a kibosh on getting a hold of jammers there. And so what I've talked about in my presentation was basically about technical means for dealing with jammers, but there's also legal means to deal with them as well. And those are having some real effect. But that said, keep in mind that there's some very serious effects that can happen when jamming occurs. You know, we just saw that with some of the results George had. And in many cases, you get HMI or hazardously misleading information. So you need to be very, very careful to have some measures in place, at least simple measures, to go off and detect this and take appropriate action. So multi-billion-dollar programs to go off and find jammers, I think those are ridiculous. But at the same time, situational awareness, I think, is very important. And then finally, keep in mind that part of the problem we have right now is that we're not effectively looking for jammers. When you look at the, for instance, the SENTINEL system, the reason the Brits all of a sudden had a bunch of jamming was because they started looking for them. And the same thing we see with the WAAS reference station. If you look for jammers, you will find them. And so they are out there and potentially quite damaging. So again, situational awareness is hugely important. So with that, I'll turn it back to demos.
All right, let's see. So we have another question, and this one is going to be for Sherman. And I guess I haven't introduced Sherman, but we'll introduce him later. But the question is, have you evaluated the effectiveness of RAIN and fault detection and exclusion algorithms required for certified GPS equipment to be a jamming solution? Or
the short answer for that is yes, we are looking at that right now as part of, not as the only solution, but part of, we think that in terms of jamming and particularly spoofing detection, you want to have a suite of detectors, and that's one of the let's say monitors that we would look at to evaluate whether we have spoofing or not. So that's part of an ongoing process right now within the FAA. They have a group called the GNSS Intentional Interference and Signal Spoofing Study Team, and they're looking at that.
All right, thanks. All right, let's see, another question here. I guess this one will go to Logan. And navigation using a variety of systems would seem to offer many benefits for civil users, but isn't this risky for military users, providing this kind of a capability?
Okay, well, you know, I'm not suggesting that military users abandon military signals such as Y code and M code. These signals, you know, they provide a lot of very important security features that play an important role in determining whether or not you've got a signal coming from a satellite as opposed to a spoof or some other source. And so they are very useful for sanity checks. But understand that jamming is not the only potential challenge. Once validated, additional signals can help by providing better satellite coverage in geographically impaired environments, for example, urban areas. They might provide better initialization for vision-aided navigation components and or other point navigation systems. And then the communications capabilities of the device provide support for assisted GPS modes. So ultimately, I would say that the gold standard of navigation will be that user device that's best able to use any and all available signals, including comm channels, to provide accurate position in a variety of challenged environments while maintaining a low probability of producing HMI. So saying that a navigation device can use only military navigation satellite signals is going to limit its capabilities in a major and unnecessary way. You know, use whatever's out there to come up with the best solution is my position on this.
All right, thanks, Logan. All right, with that, let's move on to the second half of our presentation. Before we do that, though, let's take a second poll. So, Lori, if you could put up the poll question.
Happy to do that, Demos. On the screen is that second question. In the future, when several GNSS will be operational, the method for dealing with jamming or interference will, and in this case again select just one, be standardized and uniform for all users, require different solutions for different applications, or perhaps you don't know. You can select I don't know. I'm showing 7% be standardized and uniform for all users, 82% require different solutions for different applications, and 11% weighing in with I don't know. Any thoughts on those demos?
All right, so looks like the majority, I guess the second half of the talk, you will see two different approaches, one for the marine and for the one for the aviation application, and that's kind of consistent with what the majority has answered. So different applications may require different solutions. So with that, let's move on to George Shaw's presentation on using eLoran for the marine application. George?
Okay, thanks Demos, and hello again. I'm going to talk about then the present situation and the future direction of maritime eLoran in the UK. This is going to be based on the Loran work of the US Coast Guard. The GLAs have then prototyped maritime eLoran in the UK and have recently declared the first stage of an initial operational capability with coverage of the Dover Strait. Okay, so the GLA's response to GPS vulnerability is first to harden GNSS systems against attacks wherever it can be done. But that in itself is not nearly enough, certainly not within the timescales of e-navigation. So we need to reduce the dependence of shipping on GPS by providing a second navigation system that can take over seamlessly when GPS fails. That complementary system must be technically compatible with GPS and yet wholly independent of satellite navigation. The most promising system is the US development called eLoran, or Enhanced Loran. Satellite navigation and eLoran can work together within a future ship's integrated navigation system based on evolving maritime standards for multi-system receivers. Coverage of resilient PNT in the UK and Ireland can gradually be extended, perhaps with an additional eLoran transmitter and complementary R mode from the medium frequency beacons. Now this solution can achieve such resilient positioning for ships that the GLAs can plan the careful reduction of the numbers of traditional lighthouses and buoys while still maintaining maritime safety. And the cost savings from those old age navigation will pay for the Loran service. So the UK has taken the US eLoran concept and developed a prototype eLoran system that's been working alongside GPS 24 hours a day for almost 3 years. It's prototype because it demonstrates the capabilities of eLoran using signals from the existing transmitting stations in Norway, the Faroe Islands, Germany and France. They're stations that still use the older Loran C technology. But a key element is the new UK eLoran station at Anthorn in Cumbria. It's remotely operated by a commercial contractor. Now throughout the green area shown in the centre here, eLoran can work in a differential mode, delivering 10-metre accuracy that the ships need to enter harbour safely. Over the 3 years, the transmissions have achieved very high availability and reliability. Earlier this year, the GLAs announced the launch of the first stage of initial operational capability for maritime eLoran, a high-precision service now covering the port of Dover and the UK section of the Dover Strait that you can see here. Now, maritime eLoran has several elements. The core eLoran service provides terrestrial transmissions, very strong low-frequency signals at 100 kHz. Compare this with the signals from GPS satellites, which Logan described earlier, the weak microwave signals at 1500 MHz, arriving from an orbit at 20,200 kilometers. An eLoran receiver makes timing measurements. It computes ranges to the fixed transmitters, and hence it derives latitude, longitude, and precise time. So eLoran and GPS have different frequencies, different power levels, different propagation, and no common mode of failure, and they are compatible and interchangeable in use. Variations in the low-frequency eLoran propagation delay over land from each transmitter, which are known as additional secondary factors, are mapped by a survey vessel, and these maps of timing corrections can be stored in a database for use in the eLoran receiver. In the vicinity of ports, real-time differential corrections are measured for each transmitter path. The corrections are sent to the Anthorn transmitter to be broadcast over the eLoran data channel to the eLoran receivers. The data channel also provides the integrity status and the alerts for the eLoran service. Now, in the most recent of the GLAS trials in February, GPS was again disrupted by low-power jamming on board the vessel Galatea. The vessel was equipped with eLoran and a simple processor capable of detecting GPS jamming and feeding the ship's systems with eLoran when GPS was affected. The ship's systems reverted automatically to eLoran and continued seamlessly on track during the GPS jamming period. eLoran operated multiple onboard systems, and the ship accurately reported eLoran positions via AIS to nearby ships and to vessel traffic services. Now, this was quite exciting stuff, and that seamless transition to eLoran using the IOC service was a world first, and was acknowledged by the world press with a worldwide response from the shipping industry press. This is also new that many of our colleagues don't even understand eLoran in the maritime world. They know about obsolete Loran C systems because eLoran can reuse the Loran C installations, but they confuse the two. That evolution from Loran C to eLoran is a paradigm shift. It's similar to the shift from analog to digital. And only eLoran can support all those required maritime applications. So it's early days, but here we have the new P&O super ferry that plies across the Channel and the Dover Strait, the Spirit of Britain. It's been equipped and is now demonstrating eLoran continuously and collecting long-term performance data. And into the future, eLoran equipment is being procured for 6 further differential reference stations along the east coast of England and Scotland. These will be installed by middle of 2014 to complete the initial operational capability, the IOC, so they will cover 7 of the UK's most critical ports. So the UK's eLoran initial operational capability is built on the work of the US Coast Guard, and a lot of the boxes have been ticked on the route to full eLoran. But the potential for full eLoran is still huge. In 2015, the UK government will consider whether to extend eLoran to a full operational capability by 2020 for e-navigation, extending the coverage to all ports. The GLOs hope by then that we'll be advancing step by step with US developments for resilient PNT. And meanwhile, we're cooperating with our European neighbours and seeking interoperability and compatibility with the use of the Russian Chaika system. Okay, just to summarise then, shipping is global, so the GLA's way forward is to promote the expansion of eLoran as globally as possible. There's potentially many regions to replace Loran C with new eLoran, reusing the existing Loran C stations. Now for the GLA's, eLoran is about shipping, but it can also serve cross-sector applications. It offers an economical insurance policy to support GNSS through operation of national critical infrastructures. The GLAs have set a direction here, and they encourage others to share. From an unmanned, highly reliable eLoran transmitter in the UK that you see bottom right here, there's an option to grow eLoran as the resilient PNT backup of choice to mitigate the vulnerabilities of GNSS in the US, in Europe, and beyond. And with that, I'll hand you back to Demos. Thank you.
Thank you, George. All right, so let's move on to our next panelist, and that will be Sherman Lowe. You heard from him earlier in the Q&A session first, but let me introduce him formally here, and he'll talk about the aviation side of this issue. Sherman Lowe is currently a senior research engineer at the Stanford University GPS Laboratory. He is the associate investigator for the Stanford University efforts on the FAA evaluation of alternative position, navigation, and timing, or APNT, which we'll talk about some. In this effort, he's developing aviation APNT systems that are robust to GPS interference. And his past research includes developing enhanced Loran for multi-modal use. Dr. Lowe received his master's in aeronautics and astronautics from Stanford University, as well as a PhD from the same institution. With that, I'll hand it over to Sherman. Sherman?
Hey, Demos, thanks for that kind introduction. Hello, everybody out there in the cloud. I'm going to talk about the aviation side of the business. So let's see. So aviation is moving to GNSS-based navigation in a manner similar to what George described about maritime. In fact, the FAA is basing its next generation of national airspace infrastructure, it's called NextGen, on GNSS. Europe has a similar program called CESAR. So with these programs, the airspace will be able to handle significantly higher traffic loads than today, as well as provide more efficient airline operations. And GNSS really is the key enabler. It enables many of the envisioned operations of NextGen. So we'll kind of see that in this example here. And this is an example envisioned approach for Newark Airport. And in this approach, we see three different landing approaches operating in nearly the same airspace. We have an aircraft doing a curved approach into runway 29 right, which is in Newark, while being coordinated with traffic that's landing at the other runway 4 in Newark, while flying under traffic that's going to LaGuardia Airport here. So it's a very complicated operation and really only capable with GNSS. So the loss of GNSS means loss of capacity. Some of these approaches won't be able to be done. And worse, potential loss of safety for the aircraft in these tight spacings. Its loss would affect all aircraft in the area, whereas the loss of a terrestrial navigation aid, such as an instrument landing system, would only affect one of the three aircraft shown. So compared to traditional ground navigation aids, a GNSS loss can exist over a much larger area and affect much more traffic. So that's one big concern. Another reason why GNSS outage represents a much greater concern than outages of earlier navigation system is due to its integration within the national airspace. Traditionally, communication, navigation, and surveillance, CNS, have been three separate independent systems that mutually supported each other. So even if one system should fail, the airspace can still operate safely. With NextGen, GNSS is an integral part of navigation, of course, but it's also an integral part of surveillance through self-broadcast of aircraft locations. This is known as ADS-B. And also GNSS may be used for communication timing. So this independence is no longer true. The loss of GNSS may affect multiple systems, affecting our ability to kind of mutually support each other. So as we've seen, GNSS degradation comes in many forms. So low power PPD, higher power jammers, military type jamming. And so we have to approach mitigating GNSS in the same way George described for maritime. We have to look at being able to strengthen GNSS in one way, in some sense, but also be able to deal with the fact that sometimes GNSS will be denied to us. So first is strengthening GNSS. GNSS provides significant capabilities in the airspace. We don't want to revert away from GNSS if it's avoidable. And certainly threats like PPDs, these personal privacy devices, these low power devices, while problematic, can be mitigated. In addition to GNSS itself, the FAA has examined how to reasonably make its GNSS augmentation systems, so the ground-based augmentation system, or GBAS, the wide area augmentation system, or WAAS, more robust. Several techniques are used to make these FAA systems more robust: receiver processing, sighting, system redundancy, antenna technology. We'll talk about these shortly. But strengthening GNSS doesn't mean we can prevent all outages. So we must have an alternative to GNSS when it's denied, similar to how maritime has eLoran. And so the FAA is embarking on what its alternative position navigation timing program to develop this APNT system. So let's talk about these augmentation systems and what the FAA is doing for that. So the first US GBAS system installation was in Newark. And this is delayed. The installation and certification of the system was delayed for several months by the occasional personal privacy device, PPD interference. So it's occurring along the highway. You see the GBAS antennas are pretty close to the highway. Understanding that this is potentially a common issue. Many airports, of course, are near high traffic thoroughfares. The FAA went about an effort to develop mitigations that would allow GBAS to operate in the presence of PPDs. So three major mitigations were arrived at. First, it's sighting. Let's try to put the antennas as far away from the highway as possible. It's not really feasible in Newark. It's surrounded by major roads. So the second mitigation is to look at receiver processing and to develop a GBAS ground receiver that's better capable of handling PPD outages. So that resulted in the next block of GBAS ground equipment called the SLS 4000 Block 1. And the third is to mask off the low elevation angles. You know, the PPDs are near the ground. So if we mask off the low elevation angles where jamming typically comes from, we can mitigate some of the jamming. So at Newark, the antenna heights were changed to attenuate highway-borne PPD interference. So the other system that we care about in the FAA is WAAS, the Wide Area Augmentation System. And it has many reference stations near the highway, as Logan pointed out. Fortunately, as WAAS is a widely dispersed network system, it has greater robustness to local interference and outages than GBAS, which really only has those 4 antennas at that one location. So here's a typical availability of WAAS in US and Alaska. And what we want to see is at least 99% availability in the US and Alaska for, and this is for a precision approach capability. How much PPD interference does have to occur to affect WAAS? So we looked at, in this next slide, about 100 PPDs, 10 PPDs interference per day, which is about what Logan showed in his slide before. And really, there's really no difference from the previous slide in terms of availability. And it turns out if we do the simulation and look at where the breaking point is, it ends up being about 1,000 outages per day to have any appreciable effect. So the PPD rate, at least compared to what we see today, must increase about 2 orders of magnitude to have any noticeable effect on availability. Even with that, we can still do something to mitigate the problem. The final thing to do that would apply to all our GNSS solutions would be to increase the elevation mask. A high elevation mask is a very simple mitigation. So here on this slide, you'll see the typical gain pattern of an antenna on an airplane for GNSS, and has good gain through all directions. And so the idea is that we can build an antenna that has poor gain at low elevation and reasonable gain at higher elevation. Low elevation is typically where the jamming is coming from. So this has about 15 dB attenuation there and will weaken the effect of jamming while still giving us satellites at high elevation. Of course, high elevation mask antennas lose satellites down here. So that's not really a big concern because we know we have multi-constellation coming aboard. We'll have more than enough satellites in this wedge to replace the ones that we lose there. So that's how we make GNSS stronger, but we still have to deal with dealing with situations where GNSS denied and a capable backup is needed. So APNT is about creating that capable backup. It's about using robust and improved terrestrial navigation systems to do that. In an improvement over today's terrestrial navigation system in that it complements GNSS and provides many of the operational capabilities that GNSS enables. This is not true today with all our systems. And it's important to have this capability because you want to be able to continue operations while minimizing its impact of the degradation of GNSS on the workload of pilots and air traffic. So we want to be able to continue without really causing much more work, much more safety degradation. The benefit of terrestrial is that it's much harder to jam due to both its power. It's about these terrestrial systems that we're looking at transmit about 100 to 1,000 watts, and its proximity. It's much closer than a GNSS satellite. For APNT to continue operations indefinitely in the presence of GNSS outage, it must provide full in-route coverage, as well as landing at major airports. We've identified the top 135 airports which contain nearly all the commercial traffic. And so to really attain this coverage in a cost-effective manner, APNT will have to leverage existing FAA terrestrial assets. So what are these assets? So one of the most important ones is distance measuring equipment, or DME. And DME works by round-trip ranging. First, an aircraft interrogates a DME, the DME sends a response, you get a true range from that. With 2 true ranges, you can get your horizontal position. However, because it's a two-way interaction, there are limits to its capacity. So, but it's a pretty simple system. Here's a simple DME antenna. Here's a simple DME station. The benefit of DME is that there are over 1,000 DME ground stations already operating. So there's significant infrastructure. These stations provide full in-route coverage in the continental U.S. using DME, which is positioning using multiple DMEs. Furthermore, DME's been around for 60 years, and so it's a pretty refined technology. But we can actually make DMEs better than what they are. And to do that, and we need to do that to serve APNT goals. The APNT team has been investigating many ways of improving DME. Much of the improvement can be gained from taking credit for the performance of today's system as compared to how it was spec'd out many years ago. Another one is to have more precise surveys. Current survey data may be in error to 100 or 200 meters, as that precision wasn't needed before. This can be seen here when we look at the Woodside. This is a local DME. In the survey, it uses the location of another terrestrial ground aid, this VOR, which is 60 meters from the actual DME location. You can see this error when we fly orbits around the Woodside DME, that we get the sinusoidal error, and that peak of the sinusoidal error is about 60 meters. So a lot of these gains can be made with very minimal changes. We can do further improvements if needed with newer avionics, improved signal processing, and improved ground stations. And these are also being examined by the APNT team. Another possibility is to do passive ranging from the ground, kind of like pseudolights from the ground. APNT has developed methods to providing pseudo ranges from the DMEs in a very compatible way to DMEs. So we can provide a pseudo range from these DME stations. In addition, infrastructure to support and receive aircraft broadcast position reports, these are called Automatic Dependent Surveillance Broadcasts, ADSB, may also provide pseudo ranges as well. So we get 3 pseudo ranges here. And with 3 pseudo ranges, we get horizontal position as well. And this really complements two-way ranging from DME, as it has unlimited capacity because it's passive. The problem is that you need one more station. Now, ADSB ground infrastructure is being implemented right now as we speak. It should be completed by 2013, 2014. Right now, there are 450 stations that have been installed throughout the US as of March of this year. The full deployment expects to be about 700 to 800 stations. So APNT is developing improved architectures that can use these systems in a complementary way. And so now we have a total of 1,100 DMEs, 700 ADSB, 1,800 stations to support APNT goals. Now, the one issue with doing passive ranging is that we require accurate time synchronization between stations. The prevalent way of doing this today is using satellites, in particular GPS or GNSS. In the APNT efforts, we investigate and develop civil array antenna technology for commercial off-the-shelf equipment for synchronization of these key ground infrastructures. The benefit of a simple array antenna can be taken away with this image. When Logan talked about the PPDs, they were about 100 to 500 milliwatts. And these can be powered by a simple AA battery. And they'll jam a standard GPS within 100 meters or more. Now, to do the same kind of jamming to this array antenna that was developed, you need something that has the power of roughly a microwave, 1 kilowatt, and a pretty reasonable antenna to do that same kind of jamming. And we feel that this really is a win because it limits the effect of a GNSS jamming to a very local area, so a very small outage. It also makes the jammer much easier to find. We're broadcasting at microwave power levels, we're going to find you. No problem. So the FAA efforts really has multiple levels. Furthermore, the FAA realizes there are many threats to GNSS. And so it's formed this GNSS Intentional Interference Spoofing Study Team to examine existing and emerging threats and determine the potential impact of GNSS interference in aviation, and really to identify ways to mitigate the impact of GPS spoofing and jamming, not just technical, but also legal and political and operational ways. Additionally, we're also tracking other technologies for their suitability to aviation navigation. So things like low frequency and Loran is one issue. Micro PNT devices such as small, high precision IMUs, inertial measurement systems, accurate clock, can also have significant benefits to robustness, and they can also aid APNT coverage. So the key takeaway is that aviation is taking the threat of GNSS degradation and denial very seriously, and efforts are underway to make sure that there are solutions to both current but also future threats.
All right, so before we move on to the next Q&A session, a couple of things. First, next steps. So first of all, for our audience, the PDF of the presentations as well as a list of resources will be provided at the Inside GNSS website at the link shown here. Also, if you need more information, we've on issues that have been talked about today, we have given the contact info for our sponsor at Novotel, and that could also be found on this view graph. All right, so before we move on to the next Q&A session, let's do one more poll. And if you would set up the poll, Lori.
Absolutely. On the screen is the third and final poll. Which feature of a GNSS-based navigation system is important to your applications? Again, selecting just one. Continuing to provide navigation during jamming or interference. Avoiding generating hazardously misleading information, or HMI. Or providing a timely indication of possible interference. All right, let's go ahead and take a look. And looks like 55% continuing to provide navigation during jamming and interference, 24% avoiding generating hazardously misleading information, and 21% providing a timely indication of possible interference. How do those stack up against what you're expecting, Demos?
Well, again, it looks like we have a different users from different communities in the audience. Different communities look for different features, and it's again, we have a wide spread of audience. That's kind of interesting. All right, with that, let's, I guess, move on to the final Q&A session, if we will. So the first question is going to be for George, and it's a question that comes from Susan, and it's saying, is modernizing celestial navigation techniques a viable alternative that's being considered or that's being looked at for the marine applications?
Well, I think celestial navigation is something of interest. There are a lot of possibilities that we could look at in the maritime world. But the only technology that is really here and now, that's within the timescales that we really need to implement solutions, we see as eLoran. The way that the integrated navigation system on a ship will be put in place for e-navigation will account for the potential of other sources of resilient PNT, so they could be brought into the future as things develop. And the idea of evolving a multiple system receiver with lots of different potential sources of navigation, again, would accommodate the new systems as they come along into the future. So there's a robustness and a scalability and a growth potential in the way that it's put together. But if we look at the important timescales of now, that we have a problem right now for ships, and within the next decade with e-navigation coming on board and increasing the potential problem rather than solving it, unless we have resilience, then probably eLoran we see in the UK at least as the only sensible, viable solution that's been proven.
Right, thanks, George. Let's see, the next question is going to be for Logan, and it comes from Chaz. And the question is, the crowdsourcing approach from mobile phone user GPS reception, does this require cooperative users willing to permit their phones to be used for jamming detection? If so, how should we persuade the public this is in their best interest?
Okay, excellent question there. Obviously, there's a lot of privacy issues surrounding this. First, the technical. Most GPS receivers actually generate most of the information you need in order to do the crowdsourcing stuff. Basically, they have the AGC in there. They can measure powers and so on. So then the question becomes, how do you get them to report that? And I would argue that it's in the public interest is one motivation for doing this, and to some extent, it's really a question of convincing the carriers to do this as opposed to the public. And what I mean by that is that the crowdsourcing techniques can also be used to locate and localize cellular jammers as well as GPS jammers. And so basically they can identify and locate sources of interference. So in answer to your question, how do we convince the public to do this? I think it's really a question of convincing the cellular carriers to go off and do this, and then put in place privacy measures so that you can't trace reports to a particular phone. And I think there are ways to do that as well. So hopefully that's a partial answer. Back to you, Demos.
All right, thanks, Logan. Let's see, so the next question is going to be for Sherman, and it's a question about technology acceptance cycles. That's for the aviation applications are typically quite long. Is there one technology that you think is more ready than others as an adoption for alternate means for GNSS navigation in the future airspace.
Yeah, yes. We have the same problem as George, which is we need to have ready technologies, and so that's why DME for these reasons is the near-term candidate due to the fact that it's out there, it's been out there, and a lot of planes are equipped with it. The hope for us is that we can recertify existing equipment that's already installed to actual performance levels, so that we can get some of these improved performance capabilities with no equipment changes or minimal equipment changes. And then that will give us time to allow for more advanced APNT concepts to get incorporated into new equipment and develop standards and to get fielded. And so DME really is that near-term APNT.
All right. Thanks, Sherman. Let's see, and the next question is going to be for George. And the question is, what is the projected timing and position accuracy for eLoran? And is there an estimated cost for eLoran implementation?
Okay, the accuracy of position that we're looking for is sub 10 meters, 95% horizontal. That's the requirement of the International Maritime Organization for port approach and harbor entrance. So that's a really driving figure that we've demonstrated is achievable by the differential and ASF correction services of eLoran. There is a cost to that from providing the core transmissions in the first place, and obviously also the differential setup of capital costs of equipment at ports. But those costs are within relatively small values. They're probably ongoing costs, for example, in the UK, are probably not much more than of the order of $1 million, which, if that's compared with other types of navigation systems, and GNSS in particular, is really quite small, several orders of magnitude less than GNSS. So the systems are relatively affordable and really quite capable. I should answer the timing accuracy. The timing accuracy certainly is sub 50 nanoseconds. It's sufficient to provide the stratum 1 requirement for telecommunications.
All right. Let's see. Now the next question is going to be for Peter Soar, who's also here from Novotel. And the question is, if GNSS is as vulnerable as we say it is, then why can't we just revert to paper maps and sextants for those times when we need to?
Well, hello everybody. Yeah, that's a very attractive question, but you know, firstly, I think I should say that the traditional techniques of chart or map and compass skills really should not be lost. But as we've already heard, navigators are now relying totally on radio navigation techniques, and the old skills are fading, and we see that in all walks. But I think the real point is that we're using our PNT system for things that paper techniques just can't serve, like automatic identification systems, AIS, on ships, and first-time accurate hits by complex weapons, not least to avoid collateral damage. So we really must be able to achieve a resilient PNT system to serve these needs. And I think another thing I'd like to say is that it's all about knowing when to use the reversionary mode. If you're flicking in between one and the other, and you think that one system's right, or maybe giving you misleading information, another one's not there, that area of uncertainty makes life exceedingly difficult for the navigator. So systems that can give you an indication of jamming and jamming strength, or general situational awareness, and you'll forgive me for pointing out that the Novotel gadget anti-jam system can do that for you. It becomes extremely important in this context, so that you can know which things you can rely on and which things are under attack.
All right, thank you. Let's see. Next question goes for Logan, and the question is, what strategies must be taken for the receiver antenna design for avoiding the spoofing and jamming, specifically when receivers are capable of processing multi-GNSS signals?
Well, coming back to Peter's comment, the main thing is situational awareness. And so if you've got an antenna that's using various GNSS systems out there, in some cases, you may not have coverage on all frequencies by the jammer. So as an example, you might have the very heavy jamming on the L1 frequency, but not on the L2 frequency. You might be using the GLONASS system, and perhaps there's jamming signals for GPS, but not necessarily covering GLONASS and or compass. So coming to the antenna issue, basically you're looking to have a broadband antenna system out there for your basic element bandwidth. And at the same time, you want to be operating on the various frequencies there, trying to identify whether or not there's jamming going on or not. Now, for an adaptive array, this becomes quite a challenge because antennas tend to be kind of narrowband. But I would observe that for detecting spoofing, one of the things you can do is you can compare the phase between element 1 and element 2 to identify the presence of spoofing, and there is not a requirement for low mutual coupling there. In other words, a lot of crosstalk is allowed between the antennas. And so I guess I'd have to say that this is very situationally dependent as to whether or not, well, I should say, very situationally dependent as to what requirements you've got in there. So it's a very fuzzy answer, but I'll turn it back to demos with that.
All right. All right, so the next question is for, let's see, well, I guess I could pose it to both Sherman and George, but let me start with Sherman. And the question is, we are more interested in highly accurate time information than location information. What are the alternatives for time in the event of a GPS loss? And I guess I'll let Scott and George also answer those. But Sherman, do you have something to say on that?
Yes. For synchronizing ground networks, that was one of the important things that we analyzed. So we looked across the board at different ways of doing that. Low frequency Loran is one possibility. The other possibilities are a network-based timing, such as a network time protocol, NTP, and precise time protocol, PTP. But however, those really network-based time, NTP is about a 1 microsecond system, and PTP is about NTP is about 1 millisecond system, and PTP is about, at best, a 1 microsecond type system. So if you're talking about nanoseconds, those types of systems won't suffice. People have looked at two-way line of sight time transfer. These are very good for short range, but to build out a network that operates over, say, the United States, that then becomes expensive. And so in terms of having a continental-wide system, there are very few possibilities. One is Loran, one, again, is to use satellites, but use satellites very robustly.
Yeah, if I could add another one, atomic clocks are very useful. And the caution, of course, is anytime you use an atomic clock, it's a standalone source. So you need to make sure that whatever time it has, it isn't contaminated by other sources. So you have to be very careful to make sure that you've got valid signals going into it. But atomic clocks can provide a very nice ride-through capability, because very oftentimes jamming is very transient. And we can take advantage of that by having means to survive while the jamming is going on.
Agreed.
Can I just comment on the eLoran capability in terms of timing, which because the transmissions are locked to UTC time, that distributes very accurate timing over very large areas. And the CRADA that's been going on in the US has been demonstrating that timing better than 50 nanoseconds is capable of extending to maybe 500 miles or more from a transmitter. So we're talking about continental-wide precision timing from one eLoran transmission.
Yeah, one final thing to interject is that eLoran has potentially the capability to be an authenticatable signal. In other words, you can add cryptographic components to the signal, which allows you to authenticate the fact that it's really coming from a Loran station as opposed to some spoofer or something.
Yes.
Right. All right, great. Let's see. Next question, I guess I'll direct it to Sherman, but I mean, if Neil or Peter want to answer from the manufacturer's point of view, that would be great too. The question is, how big of a challenge is it to integrate all the aviation signals discussed, each separate receiver and integration equipment, or is it how's that going to work?
Yeah, that's a very good question. That's something that we spend a lot of time thinking about, because cost of avionics equipment, and especially having to put new antennas on the airplane is a very expensive thing. And so, at least with the signals that we're looking at, they're all in the very similar frequency band. They're all in the 960 to 1200 to lower L band, megahertz to lower L band. So all of that can be received with the existing DME antenna that exists on an airplane. So that part is simple. In terms of the receiver technology, you would just think of it like a multi-frequency GNSS receiver, especially when we talk about passive ranging. And so we just have a different channel for each of the different signals that we would be tracking, and you process it a different way if it's a ADS-B-based signal versus a DME-based signal. So we don't envision it to be too hard, and that was part of the reason for the design of what we went after.
Neil, anything you want to add to that, perhaps, or no?
Sure. Yeah, I agree with Sherman there. Most of our receivers, we've thought ahead about signals coming in, certainly from the radio navigation side on GNSS, and most equipment you can take and make a composite navigation solution by adding in signals from other sources, whether that be an INS or other aiders, to go into your final navigation solution. So certainly on airplanes now, if those other sensors are already on board, it becomes a matter of sensor fusion then.
Thanks. All right, let's see. Next question comes from Richard, and it's going to be for George. And the question is, can eLoran be jammed?
Well, the first thing to say is that eLoran, obviously, as I said, is a different power and different frequency from GPS. So it's certainly not affected by the things that affect GPS in terms of jamming or solar weather. It's independently operating. It's a question that has been asked in the UK, and there's been theoretical studies to show that to jam eLoran would need a tremendous amount of power, and there have actually been real live demonstrations of that have shown that it does need a significant amount of power to be very, very close to the eLoran receiver of just a few meters. So I suppose theoretically the answer is yes, it can be jammed ultimately, but in practice it's actually very, very difficult to do. So it's a very robust system.
Yeah, if I could add to that, you'd probably see the antennas too. They're quite large.
Yes.
Yeah. If you have a small antenna with eLoran, you're not very efficient in transmitting. So you actually use a lot of power if you have a small antenna, and you would not get a lot of jamming power, and you would generate a lot of heat. So they'll light up.
Yes.
So, not a cheap jammer, not an inexpensive jammer. Okay. Thanks, George and Sherman and Logan. All right, so next one is a question from Nick, and I'm going to actually pose it to you, Sherman. And the question says, you talked about ADS-B ground stations being used as another source to provide range. What kind of signals do these ground stations provide? Do you mean the current 1030 megahertz uplink MODES or something new?
Yes, that's a good question. These ground stations actually provide a couple of different signals. So they're there to support ADS-B in terms of receiving the broadcast, but also transmitting traffic information on the ADS-B channels that the FAA has adopted. And so there are two channels for that. One is the 1090 megahertz channel, where they implement MODES extended splitter. So that's one possibility. The other channel is at 978 megahertz. It's called the Universal Access Transceiver, or UAT, and that was designed by the FAA for use by more general aviation aircraft, which don't already have 1090 installed on board. People who already have 1090 receivers, these transponders would probably go with 1090, but the UAT is for people, new adopters, and that's a channel that actually has already has a message defined that supports a pseudo-ranging capability, and it's designed to be synchronized, operate in a way that's synchronized to UTC. So there are two possibilities, and there's nothing that says you can't use both depending on what receive equipment you have.
All right, so with the, I guess we are actually, from a time point of view, we're at the point where we're going to have to actually stop asking questions. Thanks for all the questions that you asked. So with that, I guess I'll hand it over to Lori or Neil.
Thank you so much, Demos. Yes, and it is about that time, and to wrap things up, I'd like to invite Neil Guerin from Novotel to leave us with a brief word. Neil?
All right. Thanks to everybody out there for joining us today, and thanks to our panelists Logan, George, Sherman, and to our moderator Demos for an excellent presentation. Novotel is working on behalf of our customers to provide the most interference-robust solutions possible for a wide range of civil and military applications. For more info on Novotel products, including civil multi-constellation GNSS receivers, SASM receivers, our SPAN GNSS inertial product lines, and gadget anti-jam antennas, please visit Novotel online at www.novotel.com. Back to you, Lori.
Thank you so much, Neil. And folks, before we sign off, we'd like to take a moment to thank each of you for joining us and trust that you found today to be of value. Special thanks to Logan, George, and Sherman, and of course to our sponsors and co-hosts, Novotel and Inside GNSS. As I mentioned, there will be a short survey showing up at the end of the webinar. We sure would appreciate you taking a moment to fill it out. And also special thanks to our logistics producer, Patty Van Hooser, for her behind-the-scenes collaboration and support. A copy of today's webcast will be available for download, and you'll receive it in the way of a link in an email early next week. But most importantly, thank you all for joining us. This is Lori Dearman saying have a great rest of the week. Bye for now.